Hi, I'm Norman Waberger. Today we want to explore some more connections between mathematics education and rational trigonometry. In particular, we want to look at this sort of last period in high school, senior mathematics, and the role of geometry and trig. So we're kind of envisioning different kind of orientation to what we teach young people at this level. So in years 9 and 10, we've already described a way for them to learn the basics of rational trigonometry, which does not take all that much time. And then in years 11 and 12, there's a lot of time freed up for doing a lot more interesting and more in-depth study and playing around with geometry and trigonometric ideas. So my feeling is that, high school really ought to be a place where students make contact with really important things. Things that are important in the sense that they've been around for a long time in the mathematical sense. So they're kind of classical. But also, of course, touching base with modern ideas. In particular, we're going to be talking about linear algebra and the connections with that. Okay, so what I'm proposing today is just a rough kind of overview of what we might look forward to developing mathematics in the senior level years. Okay, so the basics of rational trig have been laid down, and then we can start delving into Euclidean geometry a little bit more. And a good place to start is with Archimedes' theorem, which is really a modern version of Heron's formula. So that's a very classical and important result that high school students really should see. But for sure they should see it in the context of this particular formulation rather than the traditional Heron's formula with lots of square roots. So Archimedes' theorem says that if you have a triangle like this with quadrants as Q1, Q2, and Q3, then the quadria, or the 16 times the square of the area, is exactly this kind of expression, the difference between the left and right-hand sides of the triple quad formula. So exactly the quantity that specifies collinearity of points captures, for a more general triangle, the area of that triangle. Or more precisely, the square of the area times 16. And it's useful to know that this is also the same as the product 4 times Q1, Q2 times S3. So that's connecting it also with one of the spreads. Of course, there's two other formulas just like that. Okay, so that's a nice sort of application, immediate application of rational trigonometric ideas to a very old classical thing. Okay, so now we move to some more examples of Euclidean geometry, some pretty interesting results that students can engage with, that can be illustrated and experimented with using dynamic geometry packages. So that's a really powerful modern tool that really opens up geometry to young students and really can make them so interested in mathematics. And so, for example, here's a triangle. 3 classical triangle centers: the centroid, the circumcenter, the orthocenter. These go back to ancient Greeks, and remarkably, it was left to Euler to figure out that actually they're all collinear, those 3 points. And moreover, there's a ratio of 2 to 1 here, as this diagram partially suggests. So that's really fabulous kind of thing that high school students should see. And we can study that kind of thing. We can say some things about that using Euclidean geometry together with rational trigonometry. Another good kind of thing is Chavez' theorem and also Menelaus' theorem. They kind of go together, so I'm just showing you Chavez' theorem here. So here we have a triangle and a point inside it, and then that point determines these 3 Chavian lines, and that divides the triangle sides into these sort of segments that we can call these quadrants as P1 and R1, P2 and R2, and P3 and R3 as we go around the triangle in some fashion. And then beautifully, the product of the 3 quadrants as P1, P2, and P3 equals the product of the quadrants as R1, R2, R3. So lovely kind of symmetry there. And another classical object of interest is, well, the regular pentagon, which of course is an example of a regular polygon. With the regular pentagon, we have 5 equal sides, and we have some interesting spreads that are formed by the sides, and also some interesting relations between the various quadrants that are formed. And the golden ratio kind of figures here prominently as well. So there are these two sort of golden spreads that come about, alpha and beta, which are 5 minus root 5 over 8 and 5 plus root 5 over 8. And it turns out that they are intimately connected in a beautiful way with the geometry of the pentagon. And these are also naturally connected with the spread polynomials, which are the polynomials that sort of control what happens when you repeat angles or repeat spreads in this context. And the second one is S2 of S, which is the logistic map 4S times 1 minus S. That's an example of the spread polynomial. And for example, S2 of alpha, so if you have that spread alpha and that spread alpha, then the combined spread is S2 of alpha, and that turns out to be beta. While there's beta and there's another beta, the combined spread here between this line and this line turns out to be alpha. So these two numbers have this very pleasant property that each is the other's second spread polynomial value. And the spread polynomials have all kinds of nice, beautiful properties that high school students can also explore. They're probably the most important of the many series of orthogonal polynomials around. And students should also learn a bit of circle geometry for sure, such as, for example, the subtended spread theorem, which is an important generalization of Thales' theorem. So here you have a circle, and here's a chord AB on the circle. And the statement is that if this chord AB is fixed, then this spread R here, which depends on this point C, is actually independent of C. So no matter where C is on the circle, this spread is always the same. And notably, this is actually a true theorem as opposed to the usual classical one, which is not entirely true because it depends on what side the point is with respect to AB if you're considering angles instead. Okay, so it's not true that the angle subtended is the same. It's only the same if you're on one side, you stay on one side, and it changes when you go to the other side. Notably, that's not the case here with the rational trigonometric version, which is clean and beautiful, and it's consistent all the way around the circle. The spread is always R. And notably also the relationship between this subtended spread and the spread subtended at the center of the circle, this S here, is their connection is that S is again 4R times 1 minus R, the second spread polynomial. So these are nice facts about chords and circles. Another important property of the circle is if you have two intersecting chords like this, here's AC and BD, they intersect at a point E, so we have 4 quadrants here. And it turns out that the product of the quadrants AE and EC, so this product of these two, equals the product of BE with ED. So no matter which chord you choose that goes through that point E, the product of this quadrants and this quadrants will always be the same. When this one gets bigger, this one will get smaller, and conversely. So this is a lovely fact that also suggests that this common number has some important properties with respect to the circle, and that's the start of a whole bunch of other circle geometry investigations. So these are classical things that can be derived just from basically Euclidean geometry and some rational trigonometry. So no discussion of the circle is complete without an investigation of the parameterization of the points on a circle. So here's the unit circle, x squared plus y squared equals 1. And here's this all-important rational parameterization that I talk about many places because it is so important and it's so essential that high school students learn this. Okay, and you've all seen it, I hope, at least once somewhere on my series. So here's the unit circle, there's the point -1, there's the point on the y-axis with coordinate h. You draw the line here, you find out where it intersects the circle at that second point. You call that E of h. So it depends on the h position here. H can be in this range, it could be up there, it could be down there. And no matter where it is, you're going to get a point on the circle. With the limiting value when h is actually sort of at infinity, then this line becomes parallel to the y-axis, and you actually get that point there. So here's the actual coordinates that you get by making this relatively elementary but important calculation. So e of h is 1 minus h squared over 1 plus h squared and 2h over 1 plus h squared. Okay, so it's mandatory that senior high school students learn this. Really it is. Okay, this is far more important and far more superior than the usual cosine theta sine theta story. Okay, it's a really important, try to let go of this. Okay, this is not the best way of thinking about the circle at all. You want to think rationally. It's so much more powerful. Not in all cases, and we will talk a little bit about some other situations where this happens to be more superior, namely when you have uniform motion. Okay, but if you don't have uniform motion, almost invariably the rational parameterization is superior. And of course, this also harks back to Euclid's understanding of the Pythagorean triples. This parameterization is closely connected with this kind of formula for Pythagorean triples, that if you want one number squared plus another number squared equals another number squared, like 3 squared plus 4 squared equals 5 squared, or 5 squared plus 12 squared equals 13 squared, and so on. Those kinds of triples are determined by this kind of formula here. And so if you set k equals to 1, and then you basically have this relation here after you divide by this thing here to make this thing squared plus this thing squared equals to 1. Okay, so this is really going back to the ancient Greeks and to Euclid. So it is very important. Okay, so after we've done the rational parameterization of the unit circle, we can look at the rational parameterization of the unit hyperbola, or at least one of the unit hyperbolas. The one with the equation x squared minus y squared equals 1, which is this hyperbola right here. It has these asymptotes, the lines y equals x and y equals minus x. Okay, and its rational parameterization is obtained in a very similar kind of way. You take the point minus 1 here, you take the point h on the y-axis, you draw this line that connects these 2 points, and you see where the second point of intersection with the conic is, and let's call that g of h. And then it turns out that g of h is 1 plus h squared over 1 minus h squared, and 2h over 1 minus h squared. So very similar kind of, I think the same ingredients really, but just arranged in a slightly different way. Although it's very parallel looking, there's still an important difference because the denominator here can be 0. The denominator factors as 1 minus h and 1 plus h, and that means that there are these sort of asymptotes. So that's really the origin of these red lines here, which play this important role in this kind of geometry, while they don't play a role in the Euclidean circle geometry. And this rational parameterization of the hyperbola is much better and more important than the more familiar cosh t and sine t that students usually are exposed to in high school. So there's a lot of rethinking that has to be done here, like repositioning, serious repositioning about basic understanding of fundamental things. Mathematicians as well as high school educators really need to consider these things very carefully. A lot of discussion ought to be taking place here, okay, about what is the actual better way of thinking about things. So it turns out that once you want to do calculus, you are much better off by having this kind of rational parameterization of both the circle and the hyperbola under your belt. Okay, it positions you to understand a lot of things about calculus much better. So aside from Euclidean geometry, students also want to make some contact with linear algebraic ideas, in particular vectors, and then matrices. Those are very natural and important things that can be introduced into high school, and I think they ought to be. So one good place to start is with the Archimedes' law of the lever, which just tells you where or when a lever will balance. If you have two masses on lever, when will it balance at some point? And the condition in terms of vectors is this kind of condition here, that the mass m1 times the vector v1 plus the mass m2 times the vector v2 is the zero vector. So these moments, these are vector quantities, that they all cancel out and you just get the zero total moment. That's the condition for having a balancing. Now that vector formulation of it is very pleasant because it has a natural generalization to 2 and higher dimensions. So in 2 dimensions, if you have 3 masses, m1, m2, m3, on the plane, let's say you have a triangle which is horizontal, and you're looking to see where you can balance this triangle. Okay, and there's 3 masses out there, and the rest of the triangle is, say, very lightweight material with almost no mass. Then where is that center of mass going to be so that the thing balances? Well, the answer is also exactly in terms of the same kind of balance condition, that m1 times v1 plus m2 times v2 plus m3 times v3 should add up to the 0 vector. Okay, so that determines the position of this center of mass C. And that leads to all kinds of other interesting phenomena involving barycentric coordinates especially. So once you have this idea in your mind, then you can think about, well, what happens if we can specify this point C by the masses that we need to put on the vertices in order for that to be the center of mass. Okay. So that's a very interesting kind of way of parameterizing points in the plane with respect to sort of 3 reference points. It's thinking of what kinds of masses we have to put at those points in order to put the center of mass in a particular place. If we allow negative masses, then we could even have the center of mass outside. So it's actually a very flexible kind of barycentric coordinate point of view, which high school students, again, can see, and it has lots of very fun applications. So, I'm thinking that mathematics should be really sort of enticing. It should be exciting. And when students have reached the end of high school, they should reap the rewards of all the hard work that they've done, right? They should not be bored to tears by mathematics. Sadly, today, modern trigonometry is pretty boring, I think. I have to say this, honestly. There's like all these sort of formulas, and there's a lot of memorization, and frankly, a lot of it is really unnecessary. There's really no need that students are learning that stuff. Okay, it's like ancient history. We're getting to be ancient history, and let's help it along its way, all right, by moving into the 21st century. So some of these possibilities, I think, really are empowering, or potentially empowering, and making it so much easier to attract people to mathematics. Okay, so this has been a pretty fast overview. I've gone very quickly over a wide range of things that I think would be attractive in a new kind of formulation of mathematics education, really from primary school through middle school to senior school. And I don't mean that this is going to be, inclusive, that I've included every single thing that people should study in the context of geometry. Just some highlights involving things that I think are naturally enticing. And I'd like to finish by pointing out this important thing that I think that's really a stepping stone to higher mathematics, to tertiary level mathematics, is an understanding of how analytic geometry and linear algebra can start to be brought together. Okay, this is a very important development that we need to look forward to into the future. So analytic geometry is the 17th and 18th century theory that was based on the Cartesian coordinate system, and then an understanding of curves, in particular conics, first of all. Conics, and then cubics, and then other curves, of analyzing them through their equations. Very pleasant, almost kind of remarkable discipline with like hundreds of interesting facts, a lot of which are kind of forgotten a little bit these days. And then linear algebra, the great 19th and 20th century theory, which is really a centerpiece of 20th century mathematics, involving vectors and matrices and systems of linear equations, and then other more sophisticated things. But I think that these two subjects are very close together potentially, and they really ought to be brought together. So analytic geometry needs to make a bit of a resurgence from a long period of sort of lying dormant, and it can be brought up by linking it with linear algebra. And the two things together are a very natural and potent combination. And it's really rational trigonometry that provides the algebraic orientation that allows you to see how these things naturally fit together. So once you've let go of the angles and the distance story and everything is algebraic, then those sort of tensions that have always been around with analytic geometry in terms of measurement are gone. And you can look at things in a much more balanced and fruitful way, really. And I think there's so much to be gained by looking at geometry from a linear algebraic point of view. And it also informs the direction of research also in linear algebra, that linear algebra is really a cornerstone for geometry and so important. And behind all of this is calculus, which is sort of the next step. And really linear algebra and analytic geometry are sort of foundation pieces for calculus. You really want to have those things solidly in place to really do calculus well. So I think this is something else that senior mathematics can, in general, sort of look towards and start strengthening some understanding of these things and bringing analytic geometry and linear algebra together in preparation for calculus, which I'll have to talk to you about at some other point, what I think about calculus in high school education. Okay, so in my next video, I want to talk about a missing piece to this story. You might ask, well, what about the circular functions, which are the mainstay of current trigonometry? Where do they fit in? Where are we learning about sines and cosines and tans and cotans and secants and cosecants? Well, that's a very good question, okay? And so we'll have to have some frank discussion about the role of those things and where those things actually fit in. So we'll do that in our next video. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.